Yeah, thank you, Rainer, and hello to everyone out there also from my side. In the next roundabout 15 minutes, I want to talk about the importance of the disconnector image. For the disconnector image, the position of the disconnectors is used to assign a feeder to a busbar. This is necessary to achieve selectivity in the event of a fault, which means to disconnect only those feeders that are connected to the busbar on which the fault occurred. Okay, but before we go too deep into the subject, I would like to talk about the acquisition of the disconnector position. The picture on the left side of the slide shows a double busbar with two disconnectors, one circuit breaker, and one current transformer. For each switching device, two auxiliary contacts are connected to the Cyprotec 5 device, a normally open contact and a normally closed contact. I will explain later what that means. The principle for the interpretation of the input signals is that not open means closed. The closed state is the safe state. If the disconnector is closed, the feeder is assigned to the busbar and part of the protected zone. If a disconnector is incorrectly recognized as open, this could lead to an underfunction in the event of a fault, and yet this must be avoided. The connection of both the normally closed and the normally open contact is not mandatory but recommended. With both contacts, the supervision of the running time and the binary input and supply voltage supervision is possible. A disconnector or circuit breaker provides two signals for the limit positions of the switch, the normally open contact and the normally closed contact. The normally open contact is open when it is in a de-energized state. So the state 0, which means no voltage, corresponds to the state switch open. A 1 or high signal corresponds to the state switch closed. In the information routing in Dixie, the normally open contact must be connected with a closed high to the position information of the switch, because the high state means closed. With the normally closed contact, it is the other way around. It is closed when it is in a de-energized state. So the state 0 corresponds to the state switch closed. A 1 or high signal corresponds to the state switch open. The normally closed contact must be connected with an open high to the position information of the switch in the Dixie information routing. On the last slide, I explained that the safe state is the closed state for a disconnector, because then it is assigned to a busbar and part of the protected zone. When you only connect one position signal to the Cyprotec device, use the normally closed signal. Because even when there are problems, in example with the power supply, the de-energized state is the closed and therefore the safe state. Preferably, you connect the three auxiliary contacts of the three phases in series. This is shown on the picture on the right side of the slide. This ensures that the disconnector is treated as open only if all three poles are opened. In all other cases, the disconnector is processed as closed. The first diagram on the right side of the slide shows the status of the physical switch. It changes from open to closing, to closed, and back to opening and open. In the red marked area, arcing is possible. The feedback of the normally closed and normally open contact are the final position of the switch. The normally closed contact changes its status from open to closed as soon as the disconnector starts closing, and it stays closed until the open position is reached. The normally open contact changes its status from open to closed when the disconnector is completely closed, and it changes back to open as soon as the disconnector starts closing. In the opening and closing process, both signals are 0. The running time of closing and opening can be supervised by measuring the time where both signals are 0. That means the normally closed contact is already closed, but the normally open contact is not yet open. For the running time, a maximum time span can be defined in the settings. If this time span is exceeded and something is wrong with the disconnector, you can decide by setting if this should block the protection or if it should just be reported. When the normally closed contact signals the circuit breaker is closed, the current is assigned to the busbar differential protection. This is meant with this green diagram. And yet this underlines the importance of the normally closed contact. The table on the slide shows the input of the contacts, the resulting status of the disconnector, and the reaction of the protection device. When the normally open contact is 0 and the normally closed contact is 1, the disconnector is clearly in an open state. When the normally closed contact and the normally open contact are 0 for one of the disconnectors in a bay, the state is closing or opening. The current is assigned to the busbar protection and the supervision timer is started. The normally open contact is 1 and the normally closed contact is 0. The disconnector is closed. If both contacts are high, something seems to be disturbed and a supervision timer is started as well. If there is a supply voltage failure, all position inputs of one bay have the status 0. In this case, it can be decided by setting if the last known position should be assumed or if the disconnector status should be closed. The benefits of the disconnector treatment are that there is no need of adjusted contacts and the busbar protection is active even during the disconnector transition. Okay, let's come to the bigger picture. Knowing the disconnector position, a feeder current can be clearly assigned to a busbar. In this example, there is a double busbar with 4 feeders and 1 coupler. In the first 2 feeders, the right disconnector is open, the left one is closed. The feeder current is assigned to the measuring system of busbar B. For the other 2 feeders, it's the other way around. These are connected to busbar A. The CTs are colored in red and blue, dependent on the assignment to the busbar. The coupler in this example has only one CT, and this CT is assigned to both measuring systems. With at least one CT and a circuit breaker in the coupler, you've got 2 independent measuring systems and a selective tripping is possible. In case of a fault on busbar B, the red one, only feeder 1 and 2 and the circuit breaker in the coupler must be tripped. For a fault on busbar A, it is feeder 3 and 4 and this coupler circuit breaker. In case of a temporary bus coupling by the disconnectors in one feeder, a selective tripping is no longer possible. All feeders of the coupled busbar are assigned to one preferred measuring systems. The bus zone with the lower instance number according to the engineering is preferred. The currents in the bus coupler are ignored in case of a busbar shunt by the disconnectors. Okay, before the break you already learned something about busbar differential protection and the necessity of the disconnector image. And now with a fresh mind after the break, I want to talk about check zone protection. I would like to start by explaining how the check zone works. Then I will explain the differences to the selective zone. And finally, let's look at 2 examples. Here in the slide is our well-known setup. We have a double busbar with 4 feeders and 1 coupler. In the first feeder, the left disconnector is closed and therefore it is assigned to the selective zone 2. This is the red one. In feeder 2, both disconnectors are open. Feeder 3 and 4 are assigned to the selective zone 1, the blue one. The coupler CT is assigned to both measuring systems. Now additionally to the 2 selective zone, there is a check zone. This is meant with the green dotted area. The check zone is like the overall measuring system, where all 4 feeder currents are included independently of the disconnector positions. Okay, let's go through all the bays and check their assignments. The first one is assigned to the selective zone 2 and to the check zone. That's why the CT is colored in red and green. In the second bay, both disconnectors are open, and therefore the bay is not assigned to any selective zone, but it is nevertheless part of the check zone. Feeder 3 and 4 are connected to busbar 1. That means they are part of the selective zone 1 and of the check zone. The CT color is blue and green. The coupler bay is treated differently. It is not assigned to the check zone. It is only assigned to the two selective zones and is therefore highlighted in red and blue. In general, currents flowing to the busbar have a positive sign, currents flowing away a negative sign. The picture on this slide is the tripping logic for two zones. So bus zones 1 operates if there is a trip command from the selective zone 1 and a trip command from the check zone. And of course, none of the supervision functions should be active to block the tripping. For bus zone 2, it is the same. You always need the trip signal from the check zone to release the tripping of the selective zone. According to this, the check zone protection is an additional security against malfunctioning due to problems with the disconnector image. As with the differential protection, for the check zone protection, a stabilizing current and a differential current are calculated. However, the calculation is different. For the stabilization current, you take the sum of the magnitudes of all the currents that are flowing to the busbar, and you take the sum of the magnitudes of the current that are flowing away from the busbar. The smaller of the two values is used as the stabilization current. The differential current is the sum of all currents with signs, not just the magnitudes. This slide shows the different calculation methods of selective and check zone in comparison. The difference lies in the calculation of the stabilization current. Imagine there is only one current in one feeder flowing towards the fault. For the check zone, the differential current is the magnitude of this current I1. For the stabilization current, you must compare the current flowing towards the busbar equals I1 to the current flowing away equals 0. The smaller value is 0, and therefore this is our stabilization current. For the selective zone, the differential current is also the magnitude of I1, and the stabilization current is the same as the differential current. Okay, I assume now everyone has the question of why in mind. Why is the calculation of the stabilization current different? With this slide, I would like to try to explain that. Let's have a look at the example on the slide. Imagine there's a fault on busbar 2. For bus zone 1, everything looks fine. The inflowing current is equal to the outflowing current, but there's actually a connection outside the busbar protection system in the grid between busbar 1 and busbar 2. The fault is indirectly fed from busbar 1. This is meant with the connection between the two busbars. In this case, the differential current would be the current flowing to the busbar 1 in the first feeder minus the current flowing away from busbar 1 in the second feeder, plus the current flowing towards busbar 2 equals 1 time the current measured in all three bays. The stabilization current would be 3 times this current if you calculate it the same way, like for the selective busbar differential protection. This would lead to an overstabilization and therefore to an underfunction. If we calculate the stabilization current like we learned before, the sum of all currents flowing towards the busbar equals 2 times the current. The sum of all currents flowing away equals 1 time this current. The smaller value is 1 times this current, and therefore we are in the tripping area of the check zone protection. Okay, let's look at some examples. Feeder 1 and 2 are connected to bus zone 2. Feeder 3 and 4 are connected to bus zone 1. The coupler is open, so we have two independent systems. There is current flowing towards the busbar in feeder 2 and feeder 4, and away from the busbar in feeder 1 and 3. Okay, let's put some numbers on that to make it less abstract. Let's say in bay 2, 2 kiloamps are flowing towards the busbar 2, and the same current is flowing away in bay 1. Everything is fine with busbar 2. 1 kiloamp is flowing to busbar 1 in bay 4, and the same current is flowing away in bay 3. This is also a stable, fault-free condition on busbar 1. In this case, the sum of all currents is 2 kiloamps plus 1 kiloamp minus 2 kiloamp minus 1 kiloamp equals 0. For the stabilization current, we must calculate the sum of the magnitudes of all the currents flowing towards and away from the busbar. The currents flowing to the busbar are 2 kiloamps in bay 2 and 1 kiloamp in bay 4. The sum is 3 kiloamps. The currents flowing away from the busbar are 2 kiloamps in bay 1 and 1 kiloamp in bay 3. The sum is also 3 kiloamps. So in this case, both values are equal, and therefore the stabilization current is 3 kiloamps. Okay, now let's assume there's a fault on busbar 1. The current direction in bay 3 changes. From bay 3 and bay 4, there's a current flowing towards the fault. The current in bay 1 and 2 stay the same. So the currents flowing to the busbar are 2 kiloamps in bay 2 and 1 kiloamp in bay 3 and 4. The sum is 4 kiloamp. The current flowing away from the busbar are the 2 kiloamps in bay 1. So in this case, the differential current is 2 kiloamp plus 1 kiloamp plus 1 kiloamp minus 2 kiloamp equals 2 kiloamp. For the stabilization current, you must compare the 4 kiloamps flowing towards the busbar in bay 2, 3 and 4 with the 2 kiloamps flowing away in bay 1. The smaller value is 2 kiloamps, and this is our stabilization current. These conditions would lead to a trip from the check zone. Okay, short recap. Rainer spoke about the protection algorithms of the selective busbar differential protection. I spoke about the disconnector image and the check zone protection. These three parts together are all you need to know about busbar differential protection, but you all know this is not the end of this webinar. We still have almost 2 hours, including a break and the Q&A parts. And the 7SS85 has also other very important functions, and that will be presented here as well. Rainer will now tell you about circuit breaker failure protection, and then I will come back with a part about end fault protection and the coupler differential protection.
So, as Nina already told, there's some backup functionality which are very important, and backup functionality which is really very useful to be used in a busbar protection device is the circuit breaker failure protection. As the circuit breaker failure protection takes a very big advantage of the integrated disconnector image of a busbar protection device. But let's come to the details. So, circuit breaker failure protection. What I start maybe as an introduction, we have in the busbar protection, and that's a little bit different compared to the other Cybertech 5 devices. We have two types of busbar protection. I start with a busbar protection which is common to all Cybertech 5 devices. And I will also explain about the inherent circuit breaker failure protection, which is a little bit a special type of circuit breaker failure protection only available in the busbar protection. But let's start now with the advanced circuit breaker failure protection. I have here a short example. We see here a double busbar with 4 feeders. It's a double busbar, and we have an 7SS85. It could be a centralized busbar protection, or it could be the central unit of distributed busbar protection with an integrated disconnector image. And, okay, we will start here. What is blinking here, this big error? Thanks, Nina. Here is a circuit breaker failure protection. The circuit breaker protection function which is assigned to this certain feeder here, which is assigned to bay 2. It could be a function in the centralized busbar protection, or the circuit breaker failure protection in case of a distributed busbar protection could also be assigned in the merging unit or in any modular protect 5 device. And once again, here is a 7SS85, which could be the centralized 7SS85, or which could be the central unit of a distributed approach. And we have an external feeder protection device. And this could be a protect 5 device, it could be a line differential protection, a distance protection, or overcurrent protection, transformer protection, or anything else. And this external device is detecting a fault. And it will send, you will see here the feeder protection, and this red blinking line, and together with the mouse of Nina, will send a trip signal to coil 1 of the circuit breaker. And in parallel, you see it here to this other red blinking error, it will start the circuit breaker failure protection in this circuit breaker protection function in the 7SS85 or in the merging unit of the distributed busbar protection. Then this circuit breaker failure protection will start. And what I explain now, it's really the same algorithm, the same code for all the protect 5 devices. We have a current threshold and we have a delay time T1, which is blinking here. And the device, the function is monitoring the current, whether we are above or below this current threshold. If we are below this current threshold, all is fine. The circuit breaker is working, the current will drop to 0, everything is fine. If not, if we are after delay time T1, we are still above the threshold, we will, it's a setting, it can also be used without trip repetition. Let's assume we have, according setting, a trip repetition, and then we will try a trip repetition after delay time T1. This now you will see here with this red blinking errors. And now, so typically with coil 2 of the circuit breaker failure protection, we will send the trip signal to coil 2. Okay, let's assume we try the trip repetition, nothing helps, and then we will wait until delay time T2. We will still monitor the current, whether we are below or not. If it's now maybe the trip repetition brought the result, the circuit breaker is open, the current drops below the threshold, everything is fine. If not, after delay time T2, we will have the signal trip T2, which can be used also for an transfer signal to the other end of the line to clear the fault. But we will also send, next step, we will send an internal signal directly in the centralized busbar protection, or via communication or via fiber optics from the bay unit, merging unit to the central unit. We will send a signal to the 7SS85. And according to the disconnector image in the 7SS85, which knows exactly we have the faulty feeder, the feeder with the faulted circuit breaker. Here sits this busbar 1, the upper busbar. And according to the disconnector image, the 7SS85 knows, okay, to the same bus zone, bay 1 and bay 4 is also assigned. base 3 is assigned to other busbar, so we don't have to trip it. So it will trip the associated bus zone. By the way, maybe a good idea first time to mention it here. Now the 7SS85 trips after circuit breaker failure protection bay 1 and bay 4. And in 10 minutes I will call about the inherent circuit breaker failure protection. It's important to know that also now in bay 1 and bay 4 the inherent circuit breaker failure protection will be started. That was sorry, I forgot when in Bonsab. That's the procedure, the way it works in the so-called iQuery mode. Because here we have really the current threshold of the circuit breaker failure protection. And if the current is above the threshold, we will trip the bus zone according the disconnector image. That's the iQuery mode. We have a second mode of the circuit breaker failure protection in the 7SS85. That's the so-called unbalancing mode. Most of the things are absolutely the same like what I have explained before. We have a circuit breaker failure protection function assigned to a feeder, which could be in the central busbar protection or in the merging unit. And we have the 7SS85, which is its tripping characteristic, which could be the centralized or it could be also the sender unit of a distributed busbar protection. We have once again a feeder protection device, line protection, transformer protection, anything else, which detects a fault, and it tries to trip the circuit breaker of bay 2. And once again, in parallel, it starts the circuit breaker failure protection in the merging unit 7SS85 circuit breaker failure protection function. We have once again our current threshold. We have delay time T1, watching the current information. If the current don't drop below the threshold, the device, and we have a trip repetition, the device will send a trip signal to call 2 of the circuit breaker. If this doesn't help, we will wait until delay time T2, whether the current will drop now. If nothing helps, once again, and up to now, up to before, everything the same with the same function for all the Bluetooth 5 devices. And now the enhancements of the circuit breaker failure protection for the busbar protection starts. We will send once again a signal to the 7SS85 function group busbar protection, to the 7SS85 central unit. And now we are not directly tripping according to disconnector image the bay 1 and bay 4, because we are now in the unbalancing mode. And in this unbalancing mode we are doing a different thing. We are sending a signal to the 7SS85, and in parallel you see here the current threshold. This current threshold will be sent to the 7SS85 function group busbar, to the characteristics, and this current threshold multiplied with 2 will be the minimum differential current threshold for the thing. And in parallel, the device is unbalancing, means it's multiplying with -1 the current of this feeder current. And then, via the normal algorithm with the same mechanisms of the busbar differential protections, the device is looking whether we are in the tripping area or not. Once again, it will be not the characteristic with the same minimum differential current threshold for the busbar differential protection. The minimum differential current threshold will be the current threshold of the specific feeder setting multiplied with 2. And the stabilization factor will be 0.5 every time. And then, via the normal mechanisms of the busbar differential protection, the device will trip according to this connector image, here in this example, bay 1 and bay 4. The advantage of the unbalancing mode is a very short reset time. So that means you say, even if the current drops immediately after delay time T2 has worked, and after delay time T2, suddenly the current starts to drop out. We will once again, together with sampled measured values, it's still enough. We will not wrongly trip the busbar, the complete busbar, because of this very short reset time. And okay, the reset time of the feeder protection, the reset time of the transformer protection device or anything doesn't matter. So we have really the same security as with the busbar protection device. So I know, okay. Okay, now these questions. I thought we made it at the beginning. So one question before I come to the end, and I will explain also the other functions and the inherent circuit breaker failure protection. What do you think? That's a little bit repetition of also my first part of the busbar protection algorithms. If we have this unbalancing mode, so we are unbalancing the feeder current and the circuit breaker failure protection is in the unbalancing mode, which of the algorithms, which of the three algorithms, the 1 out of 1, the 2 out of 2, or the filter algorithm, will trip after the unbalancing, after the trip 2 in unbalancing mode. So you will have around about 10 minutes to think about it, and then we will have a look to the answer. Will exercise for me how good I explained the algorithm in the part before. The circuit breaker auxiliary contact criteria for these guys who still living a little bit in the wording of the 7SS52. Here's the circuit breaker auxiliary contact criteria was called the low current mode of the circuit breaker failure protection. The circuit breaker failure protection with auxiliary contact criteria should be used in case of external force with a very low feeder current, where the current is no really trustable, reliable criteria whether the circuit breaker is open or not, especially after an Buchholz protection trip. So the acquisition of the circuit breaker auxiliary contacts will be done by the normally open and normally closed contact, just in the same way as Nina has it explained for the disconnector image. A little bit different is once again for still a lot of people who know very good the 7SS52. We had done a slightly change in our philosophy. That's because now we are really in a protection family, Cyprotec 5, whereas 7SS52 was a little bit its own world. In Cyprotec 5 and the 7SS85, the going normally open contact stops the circuit breaker failure protection, whereas in the 7SS52, the coming normally closed contact stopped the circuit breaker failure protection. That's sometimes maybe an important difference. As this is here very important, you know, circuit breaker failure protection here can trip because of a wrong signals, a whole busbar. We should use every time both the normally open and the normally closed contact to have the advantage of the supervision of the circuit breaker auxiliary contacts. And this will block automatically the CB position if it's not possible, if we are after the supervision time in the running state, or if we are in the disturbed state, if we have 0, 0. So, okay, and we have specific logic with current threshold modes for dropout applicable. Very important, because during the last weeks I have very often these questions. If you enable the auxiliary contact criteria in the Cyprotec 5, you will nevertheless every time have available also the normal current threshold criteria. So let's assume we have enabled the auxiliary contact criteria in this circuit breaker failure protection function. And we have nevertheless a current threshold of, let's say, 0.5 of the nominal current. And if we start now, if the circuit breaker failure protection has been started and the current is below the current threshold, then the circuit breaker failure protection function will work with the auxiliary contacts. But if the current at the moment of the start is above the current threshold, we will nevertheless work with the current criteria, as the current criteria is a more reliable criteria for circuit breaker failure protection. So that's also very important. It's common to Reg 5, a very important information. Inherent circuit breaker failure protection. I have already mentioned in this example, when we, after trip T2 of the circuit breaker failure protection, and according with the disconnector image, we tripped busbar as a circuit breaker in bay 1 and bay 4. And here we will start the inherent circuit breaker failure protection in the circuit breaker. So the inherent circuit breaker failure protection will start for all internal trips of the 7SS85 of the busbar protection device. Means it will start after a trip of the busbar differential protection, after the trip of the circuit breaker failure protection, after trip T2 of this one instance. So when we trip the whole busbar, and it will also be started via external trips via binary input. It can be kept also by a normal bay current. So you have, once again, the normal current threshold. You will not have a trip repetition. It makes no sense because you have tripped anyway. You will have only delay time T2. And that's important. If we are in a feeder bay, the inherent circuit breaker failure protection will provide an inter-trip signal which can be used to clear the fault at the other end of the line. So inherent circuit breaker protection start in the feeder bay, and after delay time T2, we will have the trip T2 of the circuit breaker failure protection, which can be used to send a signal to the other end of the line to trip the fault there. And if we have coupler bays, we start the inherent circuit breaker failure protection in a coupler, and we have once again the delay time T2. And here, after, if we are still above the current threshold, after delay time T2, we will unbalance the adjacent busbar to trip the associated bus zone in case of a fault of the circuit breaker in a coupler. And of course, we have also here in this case a zone selective tripping in case of the coupler bay when the inherent circuit breaker failure protection is in a coupler. There's no setting needed. You have the inherent circuit breaker failure protection in its bay, and it will, according to the configuration in the single line, in the next two sessions, session 3 and 4, we will show you how to configure with Dixie 5 a centralized busbar protection or a distributed busbar protection. And the device will recognize by itself whether the inherent circuit breaker failure protection is in the feeder bay or in a coupler bay, and will react accordingly. Bay-specific settings, of course. The current thresholds has to be adapted depending on in which feeder, in which current it's working. Inherent means also for the internal trips, and inherent for the inherent circuit breaker failure protection, you don't have to pay function points. Whereas for the advanced, for the externally started circuit breaker failure protection, you have to pay some function points, depending on whether it's a 3-pole circuit breaker failure protection or a 1-3-pole. Last but not least, circuit breaker failure protection with external circuit breaker failure relay. So that's sometimes a requirement. I know it quite well in a lot of customers in the United Arabs that they want to have their separate circuit breaker failure protection, means this whole logic monitoring the current threshold, delay time T1, delay time T2. This is all handled in an external device. And when it's finished, they only want to use the disconnector image of a busbar protection device to trip the associated bus zone. And therefore we have this functionality of the external trip in the circuit breaker failure protection. You can both use an external trip from a bay. So you will send an external trip to a bay and it will trip the bus zone where this bay is assigned to. Or you can also use an external trip directly to a bus zone. And here, common, this external trip to a bay is typically triggered by an external circuit breaker failure protection device, I have said, and it's using the disconnector image of the busbar protection. And we have the zone selective tripping, and very important what I mentioned to say, with an external trip, you should think about it, that with one binary input, that's one signal, you are able to trip a whole bus zone. That's quite dangerous, and you should really think about it, that with one binary input, it will be possible to trip a whole bus zone. And therefore, we strongly recommend to use not only one binary input, but to use also at least two binary inputs and to use this additional release contact. So typically, the external trip will come from this external feeder protection, from this external circuit breaker failure protection device, and the release contact, the release input, typically will be done by the pickup of the protection function, the pickup of the overcurrent protection or anything else, to have an additional security against wrong tripping by using this external trip.
Okay, this slide is full of facts about end-foil protection, and the details will follow then. With end-foil protection, the area between the circuit breaker and the current transformer is meant. End-foil protection is in function in the function group circuit breaker. End-foil protection is only activated when the circuit breaker is open. When active, end-foil protection removes the respective current from the selective zone measurement. And for a feeder with CT on bus side, end-foil protection removes also the current from the check zone. The circuit breaker auxiliary contact, normally open and normally closed, and the circuit breaker close command are required for this function. The treatment of the normally closed and normally open contact is comparable to the disconnector image. The normally closed contact is the important one for the position acquisition. The normally open contact is for supervision. It is important to wire the circuit breaker close command, which deactivates the end-foil protection, so that the feeder current is considered in the busbar protection. I will come to that point later. If you have the normally closed contact and the normally open contact available, the supervision of the auxiliary contacts is possible. End-foil protection requires function points. The most important points on the slide are marked in blue. Please keep them in mind at least till the end of the session. End-foil protection is only active when the circuit breaker is open. When active, it removes the current from the selective zone measurement and also from the check zone measurement if the feeder CT is bus-sided. To get a better understanding of the end-foil protection, we will go through different use cases. We start with the feeder with the CT on bus side. That means the circuit breaker is behind the current transformer from the perspective of the busbar. Then we come to a feeder with a CT on line side. And then we talk about end-foil protection in a coupler with 2 CTs and 1 CT. Okay, let's start with the feeder with the current transformer on bus side. the measuring range only goes down to the CT. So a fault between the circuit current transformer and the circuit breaker would be an external fault for busbar differential protection. The feeder protection recognizes the fault but cannot clear it because it is fed from the busbar. So without N4 protection, the fault clearance time would be delayed because you have to wait, in example, for the circuit breaker failure protection or a subordinated protection. With N4 protection, the feeder current is removed from the bus A measurement and from the check zone measurement. That means the current is set to 0 when N4 protection is active. This leads to a differential current in the selective zone A and the check zone because the fault is fed from busbar A. The differential current leads to a fast strip from busbar differential protection. That means the measuring range is extended down to the circuit breaker. Okay, now the team must show me the slides again, please. And not the results. Sorry. Okay, thank you. The second scenario we want to look at is a feeder with the CT on line side. The measuring range from the protected zone goes down to the CT. So a fault between the circuit breaker and the current transformer looks like an internal fault for the busbar A. But since the circuit breaker is already open, the fault cannot be cleared by switching off the busbar. So a bus A would operate unnecessarily. In this scenario, without the N4 protection, there's an overfunction of busbar protection, and you have to wait until the protection at the remote line side actually clears the fault. This can, of course, take some time. With N4 protection, the feeder current is removed from bus A measurement. Consequently, there is no differential current for the selective zone A and no unnecessary trip. In this use case, since firmware version 8.40, the feeder current is not removed from the check zone. The result is the same, because if there is no selective zone trip, the busbar protection will not trip regardless of the check zone. But it has an advantage, which I will explain in a moment. With the trip of the N4 protection, an intertrip signal can be sent to the remote end for a faster fault clearance time. I mentioned earlier that it's important to wire the circuit breaker close command if you have N4 protection in use. Please imagine the following scenario. We have a feeder, the circuit breaker is open, the N4 protection is active. The circuit breaker is open because there was an external fault on the line. Now there is a close command to the circuit breaker, an example from outer reclosure. Current starts flowing, but the auxiliary contacts are slower and the circuit breaker position is not yet detected as closed. That means the N4 protection is still active and the current is removed from the measuring system. For the busbar protection, this looks like an internal fault and this leads to an unnecessary trip. Rainer told me from his experience this happened like once or twice a year that the customer reported such an, in quotes, small trip. The solution is easy. The close command for the circuit breaker must be wired to the respective binary input signal closed command. As soon as the signal is received, the measured currents are made available to the busbar differential protection. What I just explained in general for a feeder, I would now like to apply specifically to the use cases CT bus side and CT line side. Then it should also be clear why we removed the current from the check zone in one case and not in the other. Let's start with the CT on bus side. The scenario is the same. There was an external fault, the circuit breaker is open. A close command is active, and the current is already flowing, but the circuit breaker is not yet detected as open. If the CT is on bus side, the current is removed from the selective zone and the check zone. That means there is a differential current for both measuring systems and the trip command is released. In this scenario, wiring the circuit breaker close command is really important. Okay, now same scenario, but a CT on line side. In this case, the current is not removed from the check zone. That means there is only a differential current in the selective zone, but not in the check zone. Therefore, the check zone blocks the release of the selective zone trip. And this is the advantage of the implementation since version 8.40. Nevertheless, always get into the habit of wiring the close command. Yeah, enough about feeders, let's take a closer look on the bus couplers. First, I want to talk about a bus coupler with two CTs. The circuit breaker is closed between them. The CTs are assigned in an overlapping mode. That means the left one is assigned to bus A, the blue one, the right one, is assigned to bus B, the red one. Therefore, the area between the two CTs, also called dead zone, is part of both measuring systems. In case of a fault on position 1 or position 2, both selective bus zones will trip. That means you have a very fast but non-selective fault clearance. Okay, now let's assume the circuit breaker was open before the fault, and the fault happens in the stub A, the area between the circuit breaker and the right CT. Without end-fault protection, the behavior would be the same as on the last slide. Both selective zones will trip. With end-fault protection, the current from both CTs is removed from bus A and bus B measurement. That means for bus B there is no longer a differential current since the current of the right CT is removed and the fault is not fed from bus B. There is no unnecessary trip of busbar B. The current measurement from the left CT assigned to bus A is also removed. But since the fault is fed from busbar A, there is a differential current and the selective zone A trips. The fault is cleared fast and selective. On this slide, a picture of a coupler with only one CT. The CT is assigned to both measuring systems. The circuit breaker is closed and fault protection is not active. A fault on position 1 between CT and CB looks like an internal fault for busbar B and like an external fault for busbar A. System B trips, but the fault is not cleared. Let's assume the circuit breaker has opened and we have no end fault protection. For bus A, nothing has changed. It still looks like an external fault. Since bus B has tripped and the fault is still there, the inherent breaker failure protection is started. Finally, the fault is cleared by the inherent circuit breaker failure protection, sending a trip command to bus system A. Now we have the same picture once again, but let's assume the end fault protection is active. Consequently, the current from measuring system A is removed, and this leads to a differential current since the fault is fed from bus A, and therefore to a trip of the selective zone A. The fault is cleared. The fault clearance time is significantly shorter than on the slide before without end fault protection. Yeah, so this is all I wanted to explain about end fault protection. Now I want to spend some minutes about bus coupler differential protection, because for a coupler with two CTs in combination with end fault protection is a very good solution for a fault in the dead zone. This slide gives an overview about the possible solution for coupler base with one or two CTs. The scenario we are talking about on this slide is a fault in the dead zone. If you have only one CT, the CT is assigned to both bus bars. This setup of fault between circuit breaker and current transformer is a bit difficult and leads to a long and non-selective fault clearance. With two CTs, you can configure the overlapping mode. That means in this example, the left CT is assigned to the upper bus in blue, the right CT is assigned to the lower bus in red. In case of a fault in the dead zone between the two CTs, both bus zones will trip. This means a very fast but unselective trip. If you have two CTs not in overlapping mode, the dead zone is not protected. This is, of course, not a solution. And yet this is the reason why we need bus coupler differential protection for selective fault clearance for a coupler with two CTs. The bus coupler differential protection protects the area between the two CTs in a coupler. This area is treated like an additional virtual bus zone, here marked in green. If you have bus coupler differential protection, the setting mode is non-overlapping. The differential current is the magnitude of the sum from both currents. In case of a current flowing through, the sign of both current is opposite and thus the sum is 0. Now let's assume there is a fault in this green marked area. Then the current is flowing towards the fault and the direction of the current in the right CT changes. This leads to a differential current greater than 0. Now in the first step, only the CT of the coupler will be tripped. After the circuit breaker is open, the current from the healthy bus zone will be zero automatically. In this example, I1C, the left CT is 0. But the fault is not yet cleared, it is still fed from bus B. And this is the moment where the end-fault protection gets relevant. I hope you remember this scenario. For bus B, the fault looks like an external fault because it is behind the CT. As soon as the circuit breaker is detected as open, the end-fault protection gets active and sets the current I2C to 0 for the busbar differential protection. This leads to a differential current and the selective bus zone 2 will be tripped. The advantage of the bus coupler differential protection in combination with end-fault protection is a selective tripping. Disadvantage is a delayed fault clearance time compared to the overlapping mode. This may lead to problems in case of high current multi-phase faults, especially when you have a network with a high percentage of non-synchronous generation, in example wind generation or solar power. This can lead to islanding or network splitting. For networks with many classic generators, slightly longer fault clearance times are usually not a problem because the inertia is higher. If you want to go deeper into this topic, we can recommend a paper that discusses this question, in which case the shorter tripping time of the overlapping mode is preferable to a selective release of the sequential tripping. Furthermore, it is possible to switch to overlapping mode for high current faults. For this purpose, a threshold value can be set for single pole and multi-pole faults. This slide shows the tripping characteristic of the bus coupler differential protection. The characteristic looks at the first sight similar to the characteristic of the busbar differential protection. On the x-axis is the stabilization current, on the y-axis a differential current. The green area is the stabilizing area, everything without color is the tripping area. As mentioned on the slide before, you can set two thresholds at which the algorithm changes to overlapping mode, one for single pole faults, one for multi-pole faults. If the threshold value parameter is set lower than the minimum differential current threshold, this results in the corresponding fault type always being clarified quickly and on an unselective basis in overlapping mode. This is meant with the lower dotted line. The upper dotted line is the threshold value for single phase fault. That means in the area between the two dotted lines, multi-phase faults are cleared in overlapping mode and single phase faults sequential with bus coupler differential and end-fault protection. In the area above both dotted lines, all types are cleared in overlapping mode. Okay, you made it till the end. I know it was a challenging session with a lot to process.